The UCEM is a collaboration between the graduate school and 10 departments in the physical sciences and engineering. Its overarching goal is to work towards increasing the diversity of our campus research community by recruiting and supporting underrepresented PhD students in STEM fields. The focus of UCEM activities is on mentorship primarily because of the apprenticeship nature of graduate education. Building a community that supports our Sloan scholars that spans across disciplinary boundaries and over department walls forms the foundation of UCEM activities. Traditions are important for building and sustaining a vibrant academic community. We are delighted that you have chosen to participate in this annual UCEM Research Summit and being a part of establishing this summit as a Duke tradition. The Research Summit provides an opportunity for us to come together as a community to learn about the questions that drive discovery in research areas supported by the UCEM. It embodies the idea that community and collaboration are central to what it means to be a scientist by providing our Sloan scholars a space to introduce themselves to the broader Duke community. You hear talks today by students who are in the second and third years of their PhD program. I thought it would be appropriate to take a moment now to pause and do a bit of reflection since we're in the middle of celebrating Black History Month. And reflecting on and zooming out a bit to consider the broader role of science and technology in society and our responsibility as scientists and technologists. Each generation has the opportunity to make scientific discoveries and technological advancements. As members of the educated elite, scientists, engineers, and mathematicians have responsibilities to the broader society. We are seeing the use of science language and the rejection of scientific process in attempts to legitimize political objectives. These are troubling times. This situation brings to mind a question that each generation should ask. What is the purpose of education? This is broader than our participation in science and our pursuits in the laboratories. But ask us as educated members of society, what is our broader role and purpose of education? I want to share with you one student's pondering of this question that I find both compelling and impressive. This comes from an article written in a school newspaper by a college student. I too often find, and by the way, I've kind of edited to remove language that implies the gender of the author. So I won't give you a hint of the gender of the author. I too often find that most college students have a misconception of the purpose of education. Most think that education should equip them with the proper instruments of exploitation so that they can forever trample over the masses. Still others think that education should furnish them with noble ends rather than means to an end. It seems to me that education has a twofold function to perform in the life of people and in society. The one is utility and the other is cultural. Education must enable a person to become more efficient, to achieve with increasing facility the legitimate goals of a person's life. Education must also train one for quick, resolute, and effective thinking. Education must enable one to sift and weigh evidence, to discern the true from the false, the real from the unreal, and the facts from fiction. The function of education, therefore, is to teach one to think intensely and to think critically. But education which stops with efficiency may prove the greatest menace to society. The most dangerous criminal may be the person gifted with reason, but with no morals. We must remember that intelligence is not enough. Intelligence plus character, that is the goal of true education. The complete education gives one not only power of concentration, but worthy objectives upon which to concentrate. This was an article written in 1948 by Martin Luther King Jr. at the age of 19 when he was a junior at Morehouse College. I first heard this many, many years ago, and it has stayed with me ever since. This is, you see, why I find it both compelling and impressive. So with that, I would turn the program over to Melissa Bostrom, who will introduce the speakers. Thank you.
Thank you so much to Professor Howell for helping us set the stage for today's talks and be thoughtful about the power of education that we will get to see on view today. So as Professor Howell said, my name is Melissa Bostrom. I am the Assistant Dean for Graduate Student Professional Development, and I am a member of the Administrative Oversight Team for the Duke UCEM. It has been my pleasure to work closely with the Sloan Scholars who will be speaking today on their presentations. We gave them a really challenging task. We asked them to share a question that drives their research, make it accessible to a broad audience, and then condense that talk to 4 minutes. Most of our scholars speaking today, as Professor Howell mentioned, are in their 2nd and 3rd year, and they will be sharing both the results that they found already, as well as some potential future directions as they refine their research trajectory. I hope that all of you will find their talks as fascinating as I have. So that we can manage our time together well, we ask that you hold your questions until the breakout rooms following the keynote address. At that time, you will have the chance to speak with the scholars about their presentations in Zoom breakout rooms. With those logistics out of the way, I'd like now to welcome our first speaker to the virtual stage, Judith Dominguez, PhD candidate in Mechanical Engineering and Material Science.
Okay, so hi everyone, my name is Judith Dominguez in the Mechanical Engineering and Material Science Department. I'm in the Payne Lab under Dr. Christine Payne. And the question that has driven my research is, can multi-walled carbon nanotubes induce pulmonary diseases? To start off, what is a carbon nanotube? So carbon nanotubes are the particles that make up a lot of the carbon materials that are used in many applications, such as electronics, materials. It's like carbon fiber that are used in sports equipment or even the interiors of our cars. It's used in agriculture to make tools, biologically, and in energy to make batteries. So these carbon nanotubes by themselves can't do much, but they can be functionalized to be able to be used in their certain applications. And to be used, they can be ground, they can go under thermal or chemical purification to be able to have that specific application and property needed. The ones I look at in my research are just the plain carbon nanotubes that haven't been treated with anything at all. So the problem with carbon nanotubes is during the manufacturing process, they are this very black powder seen in figure A. And this powder can mobilize in the air very quickly. So this is an example of it being used to make electrodes. It can mobilize in the air and contact any dust in the environment. This dust and the carbon nanotubes in the air can then very easily be breathed in by people using them, manufacturing them, or even just in the room. And we want to understand is this breathing in of the carbon nanotubes can induce or even exaggerate things like allergies or pulmonary diseases. So to be able to understand that, the goal is to understand the interactions between the proteins of our dust and the carbon nanotubes themselves as they collect on the surface. So to do this, we look at what happens when the carbon nanotubes are breathed in animal experiments such as mice. We look at the cells and what happens as they travel inside of organisms. The milestones in my project include characterizing the carbon nanotubes with spectroscopy. This is an image done with transmission electron microscopy, so imaging to be able to find the size, the density, and how they disperse in solution. Characterizing the proteins that attach to the carbon nanotubes by using different assays and gels to characterize those proteins. And finally, actually quantifying what specific proteins are present in the attachment of our nanotubes and our house dust mite coronas. So this is all works in progress as I conduct my research. So with that, I'd like to thank my lab, our collaborators at NC State, the Sloan Foundation, and NSF. Thank you.
Please join me in a warm round of virtual applause for Judith. Our next speaker is Cameron Darwin, PhD candidate in mathematics.
Okay, I will be talking about Hermitian K-theory of Dedekind domains, which will be a portion of my thesis. But the main idea of this talk isn't really about Hermitian K-theory. It's more that, to loosely paraphrase Tom Bachman, math is often accused of being esoteric and technical, and that's generally a fair accusation. It's also accused of having nothing to do with real life, and that's generally a fair accusation. So the main point of my talk is that even something as esoteric relative to the rest of math as Hermitian K-theory actually can be related in principle to things that would matter in the real world. And the core of this is that math, if you wanted to define math, the correct definition, in my opinion, would be that it's the study of analogies, and that in general, the applications are not actually quantitative. So applications you could have in mind along this route range from theoretical linguistics to computational linguistics, and the way to build this analogy is the notion of an action. So we have this core object of study in math called rings, and a ring algebraically is the structure that mimics the math we can do with whole numbers. So we can always add and subtract, and we can always multiply, but we can't always divide. So if you're allowed to add and you're always allowed to subtract, but you're allowed to multiply but not always divide, you get something called a ring. And this mimics semantically what adjectives are doing when you're describing groups of objects. So you can always compound adjectives, that corresponds to multiplying, but you can't undo that compounding. And you can always add and subtract objects in the sense of counting and including or excluding objects from a group that you're describing. So by analogy with the idea that adjectives sort of describe objects, we have this notion of an action in math where elements of a ring, which are corresponding to adjectives or to numbers, are acting on an object, which would be like describing that object. So the analog for a world with a semantics describing that world in math would be a module with a ring acting on that module. Now, the final element and the difficult element in semantics in real life is to understand verbs, but the core to understanding verbs is to understand dualities that they encode, such as active and passive voice, subject and patient, or subject and object, depending on how you want to formulate what an object is tactically, or a before or after state, depending on whether it's a transitive verb. So the corresponding answer to this in math is, how do we represent dualities on a module? And in linguistics, we might think, given just an abstract set of semantics, which a computer could see by reading in a dictionary, for example, you might ask what all the possible worlds and verbs in those worlds are available. The mathematical version of this question then would be, given a ring, what are all the modules over that ring and dualities you can put on these modules? We need to make simplifying assumptions to make this computable, but after we make those assumptions, we get something roughly called Hermitian K-theory. And also we want to study, in addition to these dualities, we want families of dualities and families of dualities and so on. These are called higher K theory. But this is a very difficult problem to solve. And even for just the counting numbers for the integers, this was only solved as recently as last year by these 9 authors that are listed. And there's some other names that should go with that also, like Weibel and Karoubi. But in general, we're very far from being able to compute this for any type of ring that's general enough to actually have something to do with real life and with semantics. So I want to be clear that this connection is very sketchy between actual proper mathematical Hermitian K theory and studying semantics. But I think that this is the type of analogy to have in mind and understanding why something this technical and abstract actually could have to do with real world applications eventually. So the purpose of studying this for Dedekind domains is essentially that because it's hard to compute, we want to get something that we have a lot of advantages and techniques available. The core thing about integers that let us compute about them is that we can factor them into prime numbers and that they're intimately related to fractions. So generalizing both of these properties gives you a slightly broader class of rings called Dedekind domains. And a concrete research goal currently is to extend the computation that looks like this table for the integers to at least extend part of this table to general Dedekind domains. So I'd like to thank my advisor, Kristen Wickelgren, and everyone else here.
Thank you so much to Cameron Darwin. Round of applause for Cameron. Our next speaker is Samantha Howell, PhD candidate in civil and environmental engineering.
Okay. Hi, everybody. I'm Sammy Howell, and my research focuses on the effect of chemically active borehole fluids in reservoir performance. So the main driver of my research is climate change. Climate change is a really big problem for our planet. And one of the leading causes of climate change is carbon dioxide emissions. There's a lot of solutions, potential solutions to carbon dioxide emissions, one of which is renewable energy. So my research focuses specifically on geothermal energy and making it an efficient and viable option for climate change solutions. So basically how geothermal energy works is you drill 2 holes in the ground, 2 to 3 holes, and you pump cold water into the ground and then use the subsurface temperature of the earth, which is super hot, to heat up that water, generating steam and electricity that you can use. So the main issue with this, like a lot of renewable energies have pros and cons, the main issue is that we don't have a good way to connect the 2 boreholes, the 2 holes you drill in the ground when they're 5 kilometers kind of under the surface layer of the earth. So my research focuses on understanding how to connect those 2 and using geophysics and the physics operating at that level to kind of make that connection. So what people have been doing so far, it's a pretty new field, but it's basically using mathematical modeling and software to understand the fractures that happen when you put enough pressure on the internal side of the borehole. So this would be the hole you drilled into the ground. And you would understand that if you pumped a bunch of water into this, the pressure would go up. And if you do the pressure enough, it goes from this gradient amount of pressure to these slip lines. And the goal here is to use these slip lines and kind of manipulate them using engineering to connect it to another borehole and hopefully get a good geothermal reservoir with a good degree of efficiency. So my specific research is looking at the pressure, and I can show you some of the models we work in my lab where you get like this pore pressure gradient increase, and then you can see that it kind of fractures off into these slip lines. And this is the benchmark test that I've done in my research so far. And I want to work with having not just water as your fluid injection, but some sort of chemical that creates a chemical reaction so you can kind of get a better channelized flow if this is connected to another borehole to kind of get that connection and work on some geothermal energy. So that's my work. Thank you all.
Thank you to Sammy Howell for your presentation. Our next speaker is Yasmin Roy, who is a PhD student in biomedical engineering.
All right, hi everyone, my name is Yasmin Roy, and today I'll be discussing how we engineered a model of our kidneys glomerulus that is personalized to you. So 15% or 1 in 7 adults in the US already suffer from chronic kidney disease. And while the 2 main causes of kidney disease are cardiovascular disease and diabetes, these patients already have a shortened lifespan of about 5 to 12 years. So scientists and clinicians are looking for ways to extend the lifespan of these patients significantly. And while there are many parts of the kidney's nephron that we can choose to study, my lab specifically focuses on the kidney's glomerulus because it's the primary site for blood filtration. And so at the glomerular filtration barrier, molecules are selectively filtered based on size and charge, first through vascular endothelial cells, through a glomerular basement membrane, and finally through specialized epithelial cells called podocytes. Now, when the doctor finds a large amount of protein in your urine, that is an indicator of significant damage to your filtration barrier. And so when you find large amounts of protein in your urine, that means that there's large holes or pores where proteins are able to escape. And so we're looking for ways to slow the progression of this damage or regenerate the filtration capacity of our kidney once again. And so while the development of these therapies has been particularly slow, partly due to a failure of animal models to translate to human trials. And so our approach now is to use human-induced pluripotent stem cells, where we can take a specialized cell of our human patient, reprogram it to induce pluripotency. And now we have a population of human cells that can continuously self-renew. We have an unlimited supply, and they also can differentiate into almost any cell type, including the podocytes and endothelial cells of our glomerulus. Now that we've differentiated these cells, we then can put them into a microfluidic device that will mimic the environment of our kidney's glomerulus, but outside of our body. And so with this device, we hope to create a U on a chip where we can develop tissue replacement therapies and regenerative medicine. We can more accurately predict your specific response to drugs, and we can also better understand how genetic diseases affect kidney development and its response. And so that's exactly what we did. On the left side, you'll see a schematic representation of our microfluidic device. And then on the right, you'll see how we seeded the cells into the device to create a model of the glomerular filtration barrier that is specific to our patient donor. Our glomerulus chip formed strong individual tissue layers of the podocytes and endothelial cells, just like you would see in a healthy glomerulus. Together, these tissues also function by physically reaching down and touching each other, in addition to depositing proteins of the basement membrane. We also evaluated whether this chip will show damage or mimic clinical damage like we would see from a known toxic drug. And that's exactly what we saw. Where we once had a strong, tight barrier, we now have large holes and pores where proteins are able to escape. And that's exactly what we quantified in the urinary channel. We saw a significant amount of urine was lost to damage. And with that, I'd like to acknowledge my PI, Dr. Samir Musa, and the co-authors of my study. Thank you for your time.
Thank you so much, Yasmin. Terrific job. Our next speaker is Daniel Santana, who is a PhD student in chemistry.
Yes. Hello, everyone. Today I'm going to be talking about my project. And the question of the project is, can we utilize photoswitchable molecules to interrogate RNA structural response to ligand binding events? So some very quick big picture background on the work our lab does. The ENCODE project showed that while 70 to 90% of DNA is transcribed into RNA, only 1.5% of RNA is translated into protein. So this non-coding RNA has been shown to be pervasive and structured biomolecules with important roles in disease processes. So RNA is now viewed as an active epigenetic pathway regulator as well as a potential therapeutic target. Currently, most small molecules that target RNA secondary structures, such as RNA bulges and stem loops. However, it's hard to achieve selectivity as RNA is very dynamic. has a limited chemical diversity and due to using the same 4 nucleobases. So it's hard for these small molecules to selectively target one RNA secondary structure over another. Moreover, RNA has a negatively charged phosphate backbone that can lead to non-specific hits based on weak electrostatic interactions between the backbone and the ligand. So small molecules that target RNA tertiary structure, on the other hand, such as the RNA triple helix, are underexplored and may be the key to achieving this selectivity. Recently, the RNA triple helix has been shown to be an attractive target as they've been implicated in different biological functions. For example, the RNA triple helix has been found to stabilize the mallet-1 long non-coding RNA from degradation, and that's shown there on the left. And of course, mallet-1 has been observed to be upregulated in several different cancer types. And to move over to bacterial systems, a triple helix is formed upon binding of SAN to the SAN2 riboswitch, which in turn sequesters the region of the riboswitch that's responsible for translation. And the triple helix is shown on the right. So there's a need to for expanding the limited set of chemical probes aimed at targeting these structures. And by harnessing the spatial and temporal control of light responsive probes, I aim to target these RNA structures to learn more about RNA structural response to a ligand binding event. To do so, I will use azobenzene. Azobenzene is a well-characterized, well-studied light-controlled molecule that can switch conformation upon UV light irradiation, as you can see in the provided example above. Azobenzene has been employed in spatial selective targeting of proteins, and azobenzene derivatives constitute several clinical candidates currently in human trials for phototherapy. The idea of azobenzene is that the light-induced shape change from trans to cis, which is shown in the provided examples, and this shape change controls what is bound. So basically, azobenzene binds in one isomer, and upon light-induced shape change, it will either stop binding or kink the target in such a way that it can no longer function as intended. The photo control potential of azobenzene's scaffold has not been explored in RNA, so applying azobenzene to RNA could shed light on RNA ligand molecular recognition, provide potential therapeutic relevant probes. So the main idea of my work is to synthesize azobenzene molecules that target RNA so we can study what happens structurally when azobenzene binds to RNA and the impact that photoisomerization has on it. So can we stabilize the triple helix? Does the RNA structure kink upon photoisomerization? And I'd be happy to discuss more of the work that I've done in the breakout rooms. And I'd like to take this time to acknowledge my lab, my PI, Dr. Hargrove, and my lab mentor, Martina. And that's all I have.
Thank you to Daniel. Our next speaker is Antonia Bruce, who is also a PhD student in chemistry.
Hi, everyone. My name is Antonia, and I'm a second year in the chemistry department, and I work in the Hargrove lab as well. And today I'm going to talk about my project, which focuses on investigating viral RNA conformational dynamics through small molecule regulation of RNA targets. So to get started, there are a variety of human diseases that are caused by RNA viruses. Some of these viruses lead to global pandemics, such as SARS-CoV-2, which is a cause of COVID-19. And to date, for many of these diseases, there are limited or no therapeutics available. For example, enterovirus 71 or EV71 causes the pathogenesis of hand, foot, and mouth disease. And previous studies have shown that there is a subdomain in the 5' untranslated region of EV71 that affects translation. Additionally, a specific small molecule, DMA135, was found to bind to the bulge and cause a conformational switch that led to repressed translation and replication. So this and other findings have provided evidence that EV71 and viral RNA can be an attractive potential drug target. However, there are some challenges associated with using RNA as a potential drug target. One of those challenges is that RNA has a very limited chemical diversity. RNA is made of the same 4 building blocks, which are called nucleotides, in comparison to something like protein that has 20 building blocks or amino acids. Additionally, RNA has a negatively charged phosphate backbone that can lead to non-specific or not selective hits based on weak electrostatic interactions between the backbone and the small molecule. So we don't hit our targeted area. Also, RNA is structurally dynamic. So RNA has the ability to form multiple different structures in different spans of time, so either very quickly or it might take a little bit longer, which can make it hard to target very specific structures. Although the structure and dynamics of RNA do make it more challenging to target, they also provide some advantages. So RNA can form secondary structures, which are defined by nucleotide pairing. And pictured on the screen are some examples, like there's bulges, internal loops, hairpin loops. And these secondary structures can actually provide sites for different ligands, such as small molecules. Additionally, studies have shown that RNA structure can influence its function. So the ability of RNA to form different structures and thus have different functions provides the opportunity to change the function of RNA through its different structures for conformation. And this is the focus of my project. I'm working to establish the properties of small molecules that can influence conformations and binding to RNA secondary structures. I plan to accomplish this by adapting a method to detect conformational changes in RNA containing a bulge in its secondary structure, in addition to considering the binding between small molecules and different RNA targets with a bulge motif and the potential to conformationally change, like enterovirus 71 subdomain as seen on the screen. And the findings of this study can be used to inform future studies on antivirals and potentially the development of new antivirals. And with that, I'd just like to say thank you.
Thank you, Antonia. Our next speaker is Kyle Pinheiro, who is a PhD student in computer science.
Good afternoon. Searching for increasingly complex patterns in large-scale biological data has required development of novel computational methods as well as novel ways of applying existing computational methods. This is the whole basis and purpose of the field of bioinformatics, and the subject that I have been investigating with the rest of the Gordon Lab over these first 2 years of my PhD. The central dogma describes the process by which genes within DNA are transcribed to mRNA and ultimately translated into proteins or polypeptides. The matter of gene regulation is largely handled by transcription factors, which determine how often or how much of these proteins get produced. They act as a kind of logical gate. They have binding sites nearby the genes that they regulate, and whether they are present or not may promote or inhibit the expression of that gene. I think it's really important to, despite the fact that I often work with sequences, purely like the text sequences of nucleotides, the reality is that all of this happens as a result of DNA and transcription factor proteins as a result of physical structure, molecular structure. And because of that, we can observe different binding behaviors for these transcription factors. And we have certain ways we express how likely a given transcription factor will bind to a particular instance of its binding pattern. In some cases, we see that transcription factor binding sites exist very near one another. And it's been established that in some cases, there can be interaction between neighboring binding sites. Particularly in some cases, the occupancy or the state of occupancy for one transcription factor binding site influences strongly whether its neighboring binding site will be occupied or not. This ultimately has an effect on gene expression. And so we care about understanding where that cooperativity does and does not exist. We have theories about what different factors this depends on, including the distance between these binding sites, whether they're on the same strand or not. But ultimately, what we want is, or one of the things we want is to be able to determine whether for a given sequence, the binding sites will demonstrate cooperativity or not. we have to start by going into the lab. We have computational methodologies that rather experimental methodologies by which we can determine whether binding sites are cooperative. But what we would really like, or what my research is focused on, is attaining computational models. This would allow us to predict cooperativity without the expense in time and financial cost of going into the lab. Very simplistically, with machine learning, we're able to take data that we've attained in the lab and run training algorithms with a model and attain a predictive model for cooperativity. We can then just introduce new inputs and attain a prediction. If we have accurate models, we can get accurate predictions, and we can even dig into that model, because we do, despite it being a black box, we care very much what's inside of it. And by investigating both the model and the results of our predictions, we can learn what contributing factors, what are the contributing factors to cooperativity. Thank you, and I will be glad to answer any questions in the breakout session after.
Thank you so much to Kyle. Our next speaker is Jalicia Amos, who is a PhD student in civil and environmental engineering.
Hi, everyone. My name is Jalicia, and today I'm going to talk about the role of nanoinformatics in assessing the environmental and human safety of nanomaterials. I am currently co-advised by Dr. Christine Hendren, and I am in the Mark Wisner lab. So first, I really want to define what exactly is nanoinformatics. And so what it is it's determining what information is relevant, and then developing mechanisms for collecting, validating, analyzing, and modeling in order to apply that information. And so if that was a lot of words, I really like to think of nanoinformatics in 3 stages. So I like to think of it first in the inquisition stage. And this is really when you're going into the lab to answer those research questions experimentally. And so this really applies to multiple different subfields of nanoscience, which includes nanomedicine and toxicology. Also includes some of the work that was presented today, including by Judith. The second stage of informatics is the informatics stage. And so what this really pertains to are the databases that are used to store the data that was collected during the experimental stage, and then the applications or the apps. So the tools that are developed to use this information that is stored. And so the last stage, the implementation of data, what all of the previous stages allows us to do is to repurpose that experimental data. And so some of the things that it can allow us to do is to use that data for discovery or regulation, or even figuring out new ways to apply these nanomaterials. So one of the things that we have done in the Mark Wisner lab is we have created a database, which we call the NIC database. And what's so special about it is that it has what we call an instance organizational structure. And so anyone who knows and understands nanomaterials understands that they are incredibly dynamic. And so what this means is that their properties in their nature change from instance to instance, or even from second to second. And so what this database structure allows us to do is it allows us to track the changes that nanomaterials go through during an experimental process. And so basically the next question is, why are we doing this? So why does any of this matters? And so what we are doing is we are gathering diverse data sets. So I have been working with both domestic partners in terms of government agencies, and I've also been working with international partners in Europe. And the goal is to have multiple data sets that none of us can individually gather on our own. And then we curate these data sets into an Excel spreadsheet format, and we curate into the same type of format which we've all chosen as the NIC database. And so what this allows us to do is it allows us to promote interoperability between databases in the US, internationally as well. And so again, the purpose is the data application. So this allows us to regulate nanomaterials better. So in the US, that's with the Consumer Product and Safety Commission, or in the EU, that's with ECHA. And it also allows us to determine the fate, the exposure, and risk assessment of these nanomaterials. And so I really want to go back to those three different stages. So the first one is the inquisition stage. So again, this is where we're in the lab answering those experimental questions. So for example, does the media properties affect a nanomaterial's fate? Or what factors really contribute most to spatiation changes? The next stage is the informatics stage. So this is all about making that data queryable, or making that data searchable and therefore accessible. And so I already talked about one of the ways we're doing that, which is with the NIC database. And then the last stage is the implementation of data. And so the next stage of my research is to build these nano tools for the nano community to access. And the goal of these tools is to be able to better determine risk and hazard of nanomaterials. So how do we design safer nanomaterials? And then how do we regulate these nanomaterials to reduce exposure risk? And with that, I would like to thank our collaborators here at Duke, and also our collaborators in the UK and in France. And I will be happy to answer any questions during the breakout session.
Thank you so much to Delicia. Our next speaker is Jaffer Vakil, who is a PhD student in chemistry.
Hi, everyone. My name is Jaffer, and today I'm going to talk about how my lab uses chemistry to build stronger, novel materials. Now, when we use the word materials, it's tempting to think of things like wooden or steel beams that can be used to fabricate homes or buildings. But things like DNA, our clothing, and even our hair all fall under subcategories of materials, which really goes to show that materials really are all around us, inside of us, on top of us, and underneath us in landfills. Plastic and rubber pollution have contributed to an environmental crisis, and one of existential nature as well, when faced with figures like thousands or millions of tons of waste being produced annually. And it begs the question, what can we do about it? The good news is a lot of things that go beyond the typical reducing and reusing and recycling. One possible chemical strategy is to fabricate materials that are designed to break down after use, so-called degradable materials. That is one possible chemical approach. The one that I am interested in is designing materials with lifespans so long that they reduce the frequency at which they must be replaced, thereby relieving their environmental pressure. Now, our lab is a little different from a lot of chemistry and materials labs, because not only do we use chemistry to make materials, but also we use physical force to run chemical reactions. And I think that the best way to explain this is by showing a video of a piece of rubber changing color upon being hit with a hammer. Now, when I showed this video to a friend, his instant immediate response was, well, so what? What's the big deal? When I hit my finger with a hammer, it also turns blue. To which I replied, fair point, but unlike the blood vessels bursting in your finger, what's occurring here is that the chemical molecule shown on the left is transforming to the brightly colored blue molecule shown on the right. And the fact that we can achieve this very specific chemical transformation with the most indiscriminate application of force imaginable by simply smashing the material with a hammer, we are able to achieve a mechanically induced chemical precision that would have been unheard of just a few short decades ago. I mentioned I'm interested in making stronger and long-lasting and more durable materials. And I'm claiming that this seemingly intimidating schematic of so-called reactive strand extension is the key to doing that. The schematic is a little subtle because it draws principles from chemistry, engineering, physics, and a few other things. This past month, I've recently gotten into rock climbing. So let's suppose that I have scaled a cliff and I'm standing tall and proud atop that cliff. But I've gotten bored of rock climbing and I want to try base jumping instead. So I cross my fingers and jump off. Disclaimer, I don't think this is how base jumping actually works. But the reason we're entertaining this ridiculous example drawn with my 5-year-old penmanship is to illustrate that at the very end of the jump, my body will experience the brunt force of it being pulled down by gravity against the rope. So we could say that I experience a high force event or a high impact event. This goes to illustrate that when a material, in this case a rope, is stressed or strained to near maximal loads, not only is the rope itself at danger and risk of being broken, but any material that is fastened to the rope, in this case myself, is also at danger of breaking or sustaining damage or injuries. I won't go base jumping, not with this rope. But what if I fabricated a rope that had little loops installed inside of it, where the idea was that once I jumped off the cliff and the rope was slightly taut, what would end up happening is that each of these loops would break open and release an amount of stored length, where the idea was the sequential release of this stored length would allow me to safely be lowered down the cliff. And it's somewhat analogous to having someone feed me bits of rope just a few meters at a time to help me descend down the cliff. This idea of releasing stored length to give some local slack along the material is identical to the chemical principle of reactive strand extension. We embed molecules that can do precisely this, release stored length, and show that these materials have improved extensibility and durability. I'm currently working not only to optimize this mechanochemical response, but also to explore how we can use this chemistry to look at different physical principles and also discover new potential mechanically active molecules. Our work's made possible by collaboration through our NSF Center Monet, our lab, and all the fantastic people at the Duke community. Thank you.
Thank you so much to Jaffer. Our final Sloan Scholar speaker for today will be Lillian Eckham, who is a PhD student in biomedical engineering.
Hi, my name is Lillian Eckham, and I am a second-year PhD student, and I currently work in the Center for Global Women's Health Technologies under Dr. Nimi Ramanujam. And today, I am going to be talking about the automation of cervical cancer detection. In May of 2018, the World Health Organization issued a global call for the eradication of cervical cancer worldwide. Though cervical cancer is largely preventable and curable, it still remains the 4th most common cancer in women today. And the most burden for the deaths and decreased quality of life due to cervical cancer falls upon low to middle income countries, countries that experience most of this burden as shown here in the warmer colors. And this is due to limited public health resources or limits to implementations of screening and treatment methods for cervical cancer. So towards this, World Health Organization specifically called for an increase of screening rates to 70% by 2030. The Center for Global Women's Health Technologies, where I work, heard this call and wanted to contribute by producing the pocket colposcope. So in traditional colposcopy, which is a screening method for cervical cancer and other diseases of the cervix is viewed from outside the speculum using a microscope, which is shown here in this setup. However, with the low cost and portable and battery operated pocket colposcope, this can actually be inserted into the speculum, and it's about the size of a tampon. It can be inserted into the vaginal wall and placed close to the cervix, and this allows for higher magnification and just a better view of the cervix itself. And so this low cost ability to view the cervix very closely can be paired with low cost assays for cervical cancer. These are shown on the right, the first of which is the application of vinegar or acetic acid, which turns precancerous cells white, and also can shine a green light onto the cervix, which highlights irregular blood vessel patterns. And with the pairing of this low cost ability to view the cervix with these assays, this produces a tool that bodes well for implementation of screening resources in low to middle income countries. So over the past few years, the pocket colposcope has actually been implemented in many places and continues to be implemented today, including here in Durham at Duke and all over the world. And with this implementation pocket colposcope, we have actually been able to grow a data set of colposcopy images that allows us to think about the next step of this project, which is what I am hoping to continue to work on. So while the pocket can allow for increased screening in these low to middle income resource areas, the next step would be to allow for diagnostics. And we're hoping to achieve increased diagnostics with deep learning tools. So the hope will be to be able to input images of the cervix with these assays, acetic acid or green light applied, into a deep learning network, which can learn relationships between the features of our images that we input, and then use what it has learned to make a final decision about the presence of a lesion on the cervix, if there is any, or maybe even identifying where on the cervix his lesion exists. And so we continue to work on this network and improve the accuracy of this network, as well as thinking of ways that we can attenuate the images that are going into here in order to increase the accuracy of deep learning and help it focus on the parts of the image that we find most important. Thank you for listening to my talk. My name is Lillian. I work in the Center for Global Women's Health Technologies, and I want to thank all my collaborators, especially the Sloan Foundation.
Thank you so much to Lillian for wrapping up the scholars' talks so well. Please join me in one more virtual round of applause for all the scholars on their talks today. They were really fantastic. Congratulations, everyone. I would now like to hand over the virtual microphone to my colleague, Jacqueline Looney, who is Senior Associate Dean for Graduate Programs, Associate Vice Provost for Academic Diversity, and the Director of the Duke UCEM. Dean Looney.
Thank you, Melissa. Thank you. I want to ask everyone to unmute briefly, and let's let these fantastic scholars hear our appreciation for what they just presented.
Great job.
This is great. I must say, Judith, Cameron, Samantha, Sammy, rather, Yasmin, Daniel, Lillian, Jaffer, Jalicia, Kyle, and Antonia. You all are just fantastic. You know, in your second year, most of you in your second year of PhD study, and you're able to share your works in progress, the things that you want to work on, in a way that those of us who are not scientists like me can really understand and appreciate the nature of your work. So thank you so much. Now, I want to introduce the speaker for today. All right. Dr. Howard Conyers. Dr. Conyers is literally a rocket scientist, earning his PhD at Duke in mechanical engineering in 2009. In his work, Dr. Conyers designs facilities for testing rocket engines at the Stennis Space Center for the National Aeronautics and Space Administration. Dr. Conyers is also a pit master from Paxville, South Carolina. For the past 7 years or so, he has been working to compile oral histories for Black pit masters across the South. He has also hosted and co-produced a show on PBS Digital Studios called Nourish, about food, culture, and the science behind what we eat. I'd like to present to you Dr. Howard Conyers.
Thank you, Dean Looney. Good afternoon, all. How you doing? I know you can't really interact like that, but thank you for inviting me to speak. Good afternoon, Duke UCEM. I'm humbled to be able to be here today. I was definitely not expecting to be invited back to Duke, but when Dean Looney reached out back in December, I couldn't say no. Not because of what she meant to me personally, but also to many students of diverse backgrounds here at Duke University. Dean Looney, you can give a master class on how to recruit graduate students of color, especially African Americans. And I'm glad that you shared some recently in the Chronicle of Higher Education, along with your retirement. I did not know that you were retiring over the holidays, and I'm filled with gratitude that you asked me at this significant moment in your life. From my personal experience with Dean Looney, you are a national leader of how to keep diverse students and to make sure they finish before it was a status quo thing to do. I remember one of my first interactions with Dean Looney, sorry, I can't call you Jacqueline, as you organized a dinner for some graduate students with Dr. John Hope Franklin, and I was one. Little did I know at that time, my offering to do recruitment at some HBCUs, as well as the University of Miami, not at HBCU, would eventually lead to Dean Looney to recommend me for a life-building opportunity while in graduate school to live with Dr. John Hope Franklin. To this day, I don't know why she recommended me, but I'm extremely thankful because his family is now my family. In addition, my son's first name is Hope, pays tribute to what he and his family means to my wife and me. Thank you, Dean Looney. I would be remiss not to acknowledge my PhD advisors, Dr. Earl Dow and Dr. Ken Hall, who I learned a great deal about being a world leader in a STEM field. And yes, they put me through it. However, I had to have grit and determination to get through the PhD work in class and when I got home. And if the mechanical engineering degree wasn't enough, I had to earn another doctorate in life and the humanities because I was being educated and mentored by another world leader in Dr. Franklin, who tested me daily on current events, and it was exhausting. During my time at Duke, I never mentioned a word of my living arrangement until he passed during my final semester, until I received an email from Dr. Dow and an email the morning afterwards. I remember at that time, Dr. Dow saying, and I'm paraphrasing, Dr. Franklin taught you things that I could not. And hearing those words from one world leader about another took me years to digest as I worked daily to become a leader. Duke teaches you how to become a world leader, but even better person, at least for me. So the duality of my life being an engineer and some say a nationally recognized barbecue pitmaster is easier because of my time at Duke. Sadly, sometimes I am no more for barbecue than being an engineer, but there is a reason for it. As I wonder what I wanted to share with you, I finally settled on a theme: bring the whole you to the world, because there is no one quite like you, and only you can deliver what the world needs. I know my bio was read, and while it may seem somewhat impressive, it is not what defined me. Even though I'm labeled as a rocket scientist pitmaster, in all actuality, I should be called a pitmaster rocket scientist, as I was cooking whole hog barbecue by myself since age 11, but I was being taught years earlier. But I'm going to give you a secret. I really built my life after Duke around being a service. When I discovered what being a service meant, things changed. Let me share with you before we get too deep a quote by Dr. King that I like. Not everyone can be famous, but everybody can be great because greatness is determined by service. Right now, you're being challenged in an environment and you're saying there are not many people that look like me, sound like me, eat what I eat, talk like I talk, or dress like I dress. However, you are where you're supposed to be, as STEM fields need you and diverse thinking to provide innovative solutions. When you come from a marginalized community, say a farm like I'm from in the corridor of shame in South Carolina, in a county that ranks 13th for worst education in the state, you are Black, you have some things to deal with. And those voices back at home need for you to speak up wherever you are to be of service to them. I'm not always saying you need to be the diversity champion, and hopefully I get this right, since he might be still at Duke. I remember Dr. Eric Jarvis telling us as a graduate students at the Boucher Society, still have the shirt. I don't know if it comes through. He told us as graduate students, meaning be careful how you pull on diversity teams, as that can pull away from your main job that your peers do not have to do. I'm not saying that diversity champion is a waste, but diversity champion has to come from people in the majority to be really impactful in my experience. As human life and experiences are not the same. So if you're not here, there could be only one perspective to provide insight into providing a solution. And while a solution may be good for one person, it may not help all people. This is where you and bringing all of you into the world matters. Being you bring insight and perspective that when combined with good research principles to find solutions or diagnose a problem could realize unimaginable results. Growing up, I was always interested in math and science, and I did not know anything about college-educated engineers until my junior year of high school. However, I was exposed to the best engineers in farmers, as my father was one, and a welder. I always enjoyed collecting farm antiques as they told a story of my parents and ancestors as baseball cards became born, and the ability to make money if I worked doing whatever, even if it was just grinding corn for chicken feed, a budding interest in entrepreneurship. Even at Duke, I wanted to take some classes at Fuqua to become more knowledgeable about business, but Dr. Dow said no, and he was right, because I needed to focus my priorities on the research during the early years. While he did say no, what he didn't know, I did explore entrepreneurship by doing it on the side. After learning a language called LaTeX, by necessity to make it easy to write a journal paper and thesis, I said, if I can write a cryptic code for this, I could learn HTML to build a website to do e-commerce, and I did. While I did not let the side business define my research, it was a learning opportunity just to give me another outlet so I would stay focused on the work. Some may call these side hustles for these times, but I like Jolene's Godfrey interpretation. All work and no play makes Jack and Jill dull. It kills the potential of discovery, mastery, and openness to change and flexibility, and it hinders innovation and invention, which I would agree. When I finished at Duke, I took a job at NASA Stennis. Part of my reason for going to work at NASA Stennis was it was NASA, but it was proximity to New Orleans. New Orleans was very unfamiliar to me, but while I was at Duke, Hurricane Katrina occurred and decimated the city. The latter reason was more about service, because I thought I could give something back to young people that looked like me as the city was trying to recover. For my day job at NASA, it started out being a structural dynamicist, where I looked at the structural integrity of components needed for rocket engine testing on the facility side and working on ways to ensure the accuracy and precision of measurements taken, particularly with flow rates and thrust loads to determine engine performance, or ISP. However, measuring flow rates and thrust loads for rocket engines is a very niche customer base, almost like the work I did at Duke in aeroelasticity, but it's critical to the world, despite anyone never seeing the people behind the work. Like in your labs, you are a service to people and mankind. Working at NASA, the diversity on the STEM side is probably better than the private sector, but it's not stellar. So I asked myself, how can I fix the problem? I thought to fix the problem we see in graduate school, we must increase the pipelines at the K through 12 level. I know going to North Carolina A&T, my alma mater, a HBCU in Greensboro, North Carolina, and seeing a lot of Black engineers was an anomaly. However, I was made aware of the lack of STEM degrees being awarded to diverse students across the board at Duke, when you look at both the undergraduate and graduate levels. But another eye-opening experience I got at Duke, I went to the National Academy of Science, and they was talking about the policy and the low numbers seen nationally in terms of diversity in a report called Rising Above the Gathering Storm. I think they've probably been working on that report for several years and looking at it, but now they call it Rapidly Approaching Category 5. At the time, I knew it was nothing I could do, but I did file the information away. Once moving to New Orleans, I said that the exposure in the K-12 was at college. I said that exposure in K-12 was important because college was too late. to get more Blacks in STEM using Black STEM professionals, as representation matters. So I created an initiative called iSTEM NOLA and being a part of a social entrepreneurship incubator called Propeller. I developed the program and learned tools about entrepreneurship, but in the quest to go after support for funding, I felt I would have to sell my soul to get grant funding where the charter school movement experiment in New Orleans was failing so many. So I completed the fellowship and stopped the program, not because the need was not there, but at the same time, Dr. Calvin Mackey also started a program called STEM NOLA. And I believe he was better positioned to address STEM issues in New Orleans as he was from that community and I was a transplant. Also, I did not want to divide up resources that could go to another person doing good work with a good model. In that moment, I also realized people and organizations gave gave money to people that they know. And if they were famous, they may help even more. So where is this barbecue thing coming from you speak of? It just doesn't make any sense. So during the year 2012, 2013, I was homesick in New Orleans for the food that I missed the most growing up on the farm in South Carolina in barbecue. The whole hog barbecue variety like you will find in Eastern North Carolina and maybe the pit in Durham if it's still open. Growing up, cooking barbecue requires a lot of people to consume, but I come from a big family. As my parents were both children of farmers, it did farming for a livelihood. During those times, they had large families. I don't know if it was to provide free labor or not to survive, but it was quite common for Black people to come from big families, especially if they was on the land with deep roots into slavery. During the holidays or family gatherings, our go-to meal was pit cooked barbecue that I could not get in New Orleans, despite having an abundance of good food. I quickly learned from trying barbecue in New Orleans, the only way to get the barbecue I was accustomed in New Orleans was to cook it myself, but it was not feasible as my family and my friend network was less than 10 people. So one day eating a po' boy, I saw a sign for a barbecue competition called Halls for the Cause, and the purpose was to raise money to support families with children with pediatric brain cancer. I said if I could cook barbecue for a good cause, which was a way of service, and get a taste of home, I am in. While my day job was not making me wealthy, I did have enough resources to field a team and support this charity. We don't have to wait to get rich to give back. Participating in this event, my name grew for barbecue, and I realized the power of social media and marketing. But I was like, why people are so interested in me? Because so many people I knew growing up cook whole hog barbecue. So as more people requested to interview me, I asked them why they wanted to talk to me. And most said, you're a rocket scientist to cook whole hog barbecue. That is quite a story. Well, some people say the style of barbecue that I cook is the holy grail of barbecue in the United States. And I too now realize it was the last vestige of the barbecue that was on the soil, on these soils over 350 years that was created on these soils when transatlantic slavery created and birthed such great traditions, even in years of darkness. The period was dark, but it should not be forgotten as slavery has occurred and is American history, not simply Black history. I know some people might say barbacoa. I consider barbacoa in Texas and what people cooking in Hawaii two different things than barbecue, and they were practiced by indigenous culture in those areas. Because I respect those traditions for what they are, and I don't want to water them down by lumping them loosely into barbecue. As from my point of view, it is mainly due to technique. The techniques of cooking barbecue and what people cook in emus in Hawaii are fundamentally different. In the back of the mind, it's important to respect those cultures. But while I was going on this journey in barbecue, I still had a day job. And also I knew I wanted to be of service. And on an application to Next City Vanguard, I said I wanted to use whole hog barbecue to make an impact on the world, while in the back of my mind, using it to expose people to STEM and efforts important to me. So I used that as my North Star, and I started embracing the duality of my life. I knew professionally, as my work in barbecue became more visible, my day job performance could not suffer. So I competed and won the opportunity to develop technology in the pilot year for NASA Early Career Initiative using agile development principles for hardware, not software. Working with the government is layered with paperwork and a lot of bureaucracy. However, to develop a HDR, high dynamic range camera project called Hydrus X, I had to rely on fusing my experiences as an entrepreneur learned at Propeller and Prior to develop technology by thinking outside of the box. I did not have any technical training in sensors, cameras, software, etc., to stitch photos together or change it down on the sensor level, but the concept of prototyping and using simulations with time in the lab helped me to get results faster with leveraging great partners that complemented my weaknesses, even though I was the principal investigator and project manager. Long story short, we produced results that went viral to share the work that NASA was doing. The work made it to the world, but I was saddened that the technology didn't make it further for reasons beyond my control with decisions made by higher ups, and not totally believing in my ability to lead it, while others did. And not all, I'm just saying. So while the technology development stopped, the all work, no play in barbecue was still going on. And during the same period, I hosted and co-produced the show for PBS Digital Studios. For the lack of recognition that I did not get professionally, I received it externally through barbecue. But however, remember, no matter what, we are human beings and we like positive recognition when we are doing positive work. However, it was a lesson for me in that moment that I needed to learn in life. During my journey, I realized similarly as Black people and other minorities were not widely recognizing STEM, I saw the same lack of representation in barbecue media. For my upbringing, it was wrong, but I did not want to bring my biases into my statements. And also I wanted to understand the history behind American barbecue because nothing I read answered my questions. And the data, the documents left did not add up to what was being told to me growing up around the fires. I knew oral history that matched some of the recorded literature, but most of what I knew or wanted to know, I had to reverse engineer or create experiments to validate the historical records. And that is what I did, because the people who actually barbecue on those plantations never told their side of the story, nor were they allowed to tell their side of the story because they couldn't read or write. The fundamentals of how to conduct research is not perfect, but it's not bad either. And so I used it in working to understand barbecue better. Learning to translate STEM fundamentals to different experiences and trials are important, but because remember, the work you are doing involves real people. For example, I had to go gather stories from my elders, and I know I could not just go get it the first time with a camera in their face, as I had to gain their trust through repeat visits and introduction, and then the recording using simply audio and not video. The trust factor is extremely important in research, especially for human beings. It's critical. And that's why you are needed, because sometimes people of diverse background could go into the community that they could talk to in a certain way that only the people in that community can understand. Through engineering and barbecue work, I'm seeing the possibilities of things I want to do as endless. While my objective in barbecue is to amplify the work of Black and brown voices, I'm also able to do it through Southern food and farmers and related projects, whether it's my 100-acre project, which is an agricultural-based manufacturing incubator to help preserve Black-owned farmland that I hope I can transition into a research institute when I transition from NASA one day. Or Conyers Family Barbecue, a media and production company to tell stories to educate all. Then when I have more time freedom, I will work and continue to educate, but I may want to teach special lectures using barbecue as the subliminal draw, like partnering with universities that may want to look at the computational fluid dynamics of barbecue, such as looking at airflow over a brisket, or examining American history through barbecue. Who knows where the barbecue journey will take me, but I'm taking it for a ride. Currently, professionally, I work with NASA Small Business Technology Transfer, STTR, which works with small businesses and universities as is a congressional mandated program to provide early stage funding to help solve some of the agency technology needs. The thing I like about STTR is that small businesses are required to work with research institutions like universities versus SBIR, which only requires the small business. NASA is one of several federal government agencies that have STTR opportunities that may be more in line with your areas of research. I know for sure the USDA and the Department of Defense have opportunities at STTR, but there's a few others. Currently in barbecue, I'm working on a book on the illustrated history of American barbecue, which I'm writing. And I am working as a mentor for Kingsford Charcoal Preserve the Pit program, where I developed the framework for this mentoring program. Both of these projects are important to me because they educate. I am of service and is also investing in the future of barbecue. Hopefully by now, you see why I believe in bringing the whole you to the world. Only you can provide your gifts to the world. Maybe one day through my work in barbecue, some funders will give me the resources to use barbecue as a vehicle to share the message of STEM to hopefully increase the pipeline without having to sell my soul in the process. I'm not giving up on that goal because every day I realize the STEM community needs diverse representation and they need to be encouraged to stay. Even if I'm not able to fund it, or even if an organization doesn't want to fund it, I will figure out a way to fund it myself. However, there's an old African proverb that says, if you want to go fast, go alone. If you want to go far, go together. Thank you, Dean Looney, Duke University UCEM, and the Sloan found me to speak to your graduate students at this time in my life. I really hate that I couldn't do it in person, but this thing called COVID forced us all to pivot and adapt. Maybe when we could all are able to safely reconvene in person, maybe because we all are human beings. We have to remember that even though we are STEM professionals, maybe we can eat some barbecue, have some spirits, and have a good time. Thank you again.
Howard.
All right, everybody, mic's off. We need a round of applause for Dr. Conyers. That was great. And I hope you can cater this event when we get together. You've made me so hungry just listening to this.
Yeah, I don't cook as much anymore. I cook very special occasions though.
Hey, we're special. All right.
Y'all are special.
I think we have time for a few questions, and then I'm hoping Dr. Conyers can come to the breakout rooms and talk to the scholars. Any questions before we move on? I've got one, and that is, how did your training in MEMS prepare you for these two careers that you now have?
I mean, honestly, like, so as any researcher, you spend a lot of time in the library before you even go into the lab. And so I was forced to start reading all kinds of books to kind of get a basis of everything on the literature. So I had to do a literature review. Then, and also as a MEMS person, you have theory and you have experimentation. So if you saw something in the literature, you want to validate the processes. So in doing that, I went through and set up experiments. I cooked in the ground, I cooked above ground, I cooked every domesticated farm animal in the American South that was in the literature, ranging from a hog to a whole cow. And so I designed a pit to actually cook a cow. So I mean, MEMS was very important to it. And then the informal training I got from Dr. Franklin, I didn't want to have anybody to challenge my research. And also I didn't want anybody to challenge my research from a MEMS perspective. I mean, I was trained by Dr. Earl Dow and Dr. Kenneth Hall, and those are two individuals. I'd never seen anybody challenge their research, and I didn't want anybody to challenge my research. So I started reading not only like barbecue books, I read books on American history, I read books on capitalism, so I could look at the maps. I read books on like cartography. I kind of did all kinds of stuff. I traveled across the South, the various states. I went to Eastern North Carolina down to Aden. Then I went to Arkansas. I went to Mississippi. I spent time in the archives, in the digital archives online to look at pictures. I looked at illustrations. I did a lot of work. I probably almost got an informal PhD, but I also understand American history through going through to understand the barbecue story. And it just was a lot of work. I mean, it's probably about 8 years of my life.
Yeah, it sounds like an incredible amount of work. Very successful, though. It's amazing. And I'm wondering, just a follow-up question on that is, how does your current passion barbecue and the whole culture around barbecue. How does that play into your job at NASA?
I generally keep both of those things separate, but what I have learned being involved in the food side, the food media side, a lot of scientists and technology, a lot of people in the STEM fields are not great communicators. And what I mean, they're not great communicators with the people who need their product, or even when they get to go market their product or sell their product or tell a story. And so I will say that is one of the major things I got from working in the food media, is getting better at telling stories about the products that I'm designing as an engineer. And I think that is something that I will leave with all the graduate students, professors. Like, you could develop great technology in the lab, but if you can't tell it to anyone, then it's just kind of like it's a moot point. I don't know if that answers your question, John.
It does. Yep, absolutely. Courtney, you have a question?
Okay, well, wonderful talk. I just wanted to mention your point that you made about, trying to balance your multiple interests and also making progress on your doctoral degree. And I think that's such a very important point, because a lot of times in your academic world, with the PhD, you're hearing focus, 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 and you're kind of getting, you're narrowing down, your expertise. But at the same time, we're not, unifaceted people. So do you have any advice for the Sloan Scholars in terms of how to understand, how to kind of keep that balance so that you're still making, the progress you want to make towards your academic, your doctoral work, but also, keeping the other parts of that whole part of you, you're able to bring that wholeness of you to the world. Do you have any advice now for how to balance that?
I mean, so first and foremost, you have to always remember where you are currently. Like, you're currently at Duke to get an advanced degree. So that's always priority. But if you don't find a way to counterbalance what you're doing, you're going to burn yourself out. And it doesn't matter whether it's in the STEM fields, just professionally, you have to find something, some outlet. One of the outlets I found during COVID, which is sad to say, was I realized I need to exercise more. And so we have to do little things to take care of ourselves and to work both sides of our brains, because working the other side of the brain is important too, because we're human beings and we still need these relationships. And if we're developing a technology or doing some medical research and we don't know the implications into a community, then we also we're doing a disservice to the people who really needs this. So I think you just have to find it, but you have to know what is your number one priority at the time and get through the process.
Dean Looney, do you have a question?
Yes, Howard, thank you so much. For those of you, for the students who don't know, because I mean, I don't know if some of you were born, when maybe, I don't know, you guys are young, but Howard talked about John Hope Franklin, one of the world-renowned historians in this country. And I hope you all will, once you get off Zoom and start Googling books by John Hope Franklin. It's very important. It was very significant that Howard was able to spend the time helping with Dr. Franklin's care, during his declining years. That was very, very important to do. And it was even more important that it was a Duke student that he wanted to help him. So that was significant. So Howard, as a graduate student, and of course, I know things about graduate students that I'll never tell. I'll never tell some of the things that many of our students go through during their journey, as many of our scholars. But the thing now is, and it was then, and it will always be, the isolation, the anxiety, the depression that comes with trying to get something called a PhD. It's really hard. And you were at Duke during a time where we didn't have the number of students of color that we have today at Duke. So can you just say a little bit about, how you got through and how you took care of yourself and how you managed your own well-being?
I think so, Dean Looney, that's a good point. So in the STEM fields, we did we were able to form a community. There was an organization called the Boucher Society. And we used to have, I can't remember if they were monthly meetings, and we had time away from the class. And so that really helped with some of the isolation with somewhat, but also because I went to school in Greensboro, I had a connection back to, I could go back to North Carolina, I would go back to Greensboro on occasions, and not being too far from home. If I really get down into the dumps, then I will go back home. And I know that's a hard thing to do too. But what I would encourage people at this time, and I think one of the biggest things I wish I did more, and I did it quite a bit while I was at Duke, is experience the other cultures. Go have dinner with people who don't look like you. And I'm not talking about white people, just people of color, and let them order the menu items. Like you just say, if you don't eat pork, I know one time I went to this Chinese restaurant in Durham with some of my people in MIMS. And they ordered a menu, and I'm pretty sure it was nothing on the menu, and I just went with it. And the food was amazing. Went to a couple of Thai places with people. I experimented with sushi for the first time while I was in Durham, and I still love sushi, but my parents and raw sushi, not cooked sushi. But I think we just have to figure out, we really need to take time to learn about the other cultures, because the world is very global. And it's going to get even more global, but the world gets very small too at the same time. As I'm getting older and getting farther away from Duke, I realize in life is just, you probably 2 or 3 degrees of separation from anybody you want to know, especially now with this thing called social media, these phones, whether it's TikTok, Instagram, the world is getting even smaller. To be able to connect with people all over the globe. I mean, I went to West Africa one time, and I went to Ghana, and some people took care of me based on the work they seen, but that wouldn't have happened in 2009 when I was at Duke. So really I think really get the time to know people. And I think that's always important. It never fails.
Is there anything that you wish that you had gotten to do during your time at Duke that maybe just because of time constraints or for any other reason ended up falling through? And I guess if I could make the question a little broader, I think as PhD students, or just grad students in general, we often always struggle with time management. Over the course of your careers, has there ever been anything that stood out to you about how to manage your time and how to really make time for what's really important and what matters to you?
So I think the one thing I didn't take advantage of, my wife now was in South Africa, in Johannesburg. And I thought all I had to do was the research. And I regret that experience, not going to spend 2 weeks down in Johannesburg to this day. And I think that even before I got to graduate school, the thing that I really regretted the most about my whole college and graduate school career is I never went to study abroad. And I know it's hard to do in the graduate school process, potentially just because of the constraints of the research and depending what kind of work you're doing. But that is probably my biggest regret, not taking a trip to South Africa with my wife. Not my wife, just to kind of experience another culture. All I had to do was buy a plane ticket. And I just got so caught up in the research that I just I can't do it. I got to focus on it. But now in hindsight, I should have went. And so that would be my biggest thing.
Again, thank you, Dr. Conyers.
Thank you.
That's some applause.
John, I just want to acknowledge that one of our Sloan Foundation colleagues has been on listening, Denise Ellis. And I just want to say thank you for joining us. And also, Howard, one of your extended family members, Karen Roberts Franklin, is on. A daughter-in-law of John Hope Franklin has joined us too. Thank you, Karen, for joining us. This is the upside of being in a virtual space, that folks who couldn't be with us are able to join us. So thank you both for joining us this evening.
Well, speaking of thanks, let me just make a few, and then we'll move to the breakout rooms. First of all, I'd like to thank the Sloan scholars who spoke today. It was really amazing, and you were well coached by Dean Bostrom. This is world-class professional development you got. Lessons that will be useful for every presentation you give for the rest of your lives. And it worked because they were very good. I really enjoyed them. And in fact, you took me back to when I was a first-year PhD student and I was in a comparable kind of university, comparable kind of, experimental science program. And I was at a kind of a conference listening to second and third year students talk about what their projects were. And similar to you guys, they had projects, but they, didn't have all the answers yet. And I remember thinking, well, I can tell that these things are all really good and they're exciting. I don't understand every word, but I can tell these people are going places. And now I have a few years out from my PhD, and I can see that those people have become truly leaders in their fields. One of them even got a Nobel Prize last year, Jennifer Doudna. So it's the same way. I feel exactly the same way now, that I didn't understand everything about every one of your talks, but I can tell you guys are going places. And here to our Sloan scholars, much appreciated. I'd also like to thank our Sloan interns, Carla and Wen, for their great work in preparing for this summit and helping organize it and run it, and Tish Futrell in particular for being the mastermind for getting this done. Very grateful for all of their efforts. But before we go to the breakout rooms, I think there's one last thank you that I really want to give, and that's to Dean Looney, because I don't know if you all know that it was really Jacqueline Looney who was the mastermind and the instigator of the whole Sloan UCEM concept at Duke. She literally, from the very first word that was written down, even before the first word was written down, the first thoughts that were given to how Duke might be able to partner with Sloan to develop something really, really fundamentally different from the way we've done things before. That was Jackie Looney. And she recruited a team that includes me and many other people. We've all been thrilled to be on it. And she's been the driving force for the UCEM ever since. And so a huge thanks to Jackie Looney, as this is her, I guess, her final Sloan Summit as an associate dean, but hopefully she'll come back as a guest.
Well, I get to recruit one more class, and that's the cohort. And I am going to be asking all of my Sloan scholars to help me get to 10. You hear that, Denise? We're going to get to 10.
We're going to get to 10.
Which means in the fall, or maybe I should say y'all, we will have 50. Yeah, thank you, John.
50 thanks to you. And personally, I would just like to say how much I've enjoyed working with you on Sloan and every other project, and I've learned so much from you. So here's to Jackie Looney.
John, I think we should unmic our mics and give Jacqueline a round of applause.
Yes, let's do it. Unmute and applause.
We're gonna miss you.
All right, thank you. So let's move now to the breakout rooms.
I'm going to ask our PI, Professor Howell, to close us out. And I just want to say again, another big thank you to the scholars. I could not have done a presentation on the work that I was doing on moral development and ego in 4 minutes. I just couldn't have done that. I'm totally impressed by the quality of the work. And I just want to thank Wynn and Carla for also helping Melissa to get this going. It was great. And Howard, thank you so much. Your story resonates with so many of us, your journey and your ability to tell your story in a way that I think that many of us are just going to be thinking about, the things that you've shared. So thank you so much.
First of all, just want to thank everybody for coming out today, making this one of Duke's traditions. Summits are as much scientific as change as they are social. These are how you make connections that sometimes last a lifetime. And we hope the scholars will use this and follow through on it with the connections that they make. And we're so happy that they get this opportunity to introduce themselves to the broader Duke community. And I personally want to thank Dr. Conyers for his presentation. You don't know it, but some of your words just made my spirit soar because they resonated so much with my personal journey. Just ahead of you, maybe 30 years or so, but the journeys were so similar. And I thank you for especially the message that we should bring our whole selves everywhere we go because we are unique. The whole theme of service, how can we be service to each other, resonates to so many of us. And we just thank you for those words. And thank you for not making it a science talk about rocket engines. I appreciate it. And I will give you a personal confession. I know I'm taking too long to close out, but some time ago when my children kept us so busy, I traded in my charcoal grill for a gas grill. But it's long overdue for a new grill, and I might go back to charcoal and, you know, inspired by your words and your love of real barbecue. So, and so with that, I just want to thank all the organizers of this summit. We thank, of course, the sponsors, Duke University, the Sloan Foundation, and all who contribute to make UCEM what it is. And with that, thank you very much. I hope all you enjoyed the summit, and we'll have a good evening. Bye-bye.